Okay, so I'm giving a retrospective of the work we've done here at Sensem over the last 7 years. And there are a few bits that we're still working on now that you won't see yet. And Gonzalo Carrasco will introduce that in the next talk a bit. But we've had a lot of people involved, and there are actually many others I'm not listing here because they're not involved with the work that I'm showing here today, but they're involved with the work that we're doing presently. Okay, so when I was first asked to possibly participate in Sensem, I looked around at things I knew about and could possibly find a research focus on. And I said, with Singapore, well, what could I do that's relevant to Singapore? And so I thought, well, I work on coral reefs, as you'll see. And here we are in the middle of a lot of coral reefs, so it was an appropriate thought to think about that. So that's the starting point. And of course, Singapore is not only surrounded by many regions that have coral reefs, but it has many of its own. And there are people here that we've cooperated with who are studying corals, so it was a good collaborative point. Okay, so why study metals, isotopes, and paleoclimate in Singapore corals? First off, there are metals such as lead and cadmium that are toxic and at high levels hazardous to marine life and humans who eat those, the seafood. But there's a problem that it wasn't until the late 20th century that scientists developed the ways to measure trace metals in seawater. And so if you go out to Singapore Straits now and measure any trace metal, you have nothing to compare it to. We don't know what it was 100 or 200 years ago. So you're really just sort of left in this vacuum of not really knowing, has it gone up, has it gone down? You don't know anything. And so we can't use historical data. And as you'll see, annually banded corals do record past concentrations of metals in the ocean. And so we can establish the evolution over time. And basically, for this engineering-focused group like Sensem, I think we're putting chemical sensors into a time machine. So we're putting sensors that go back 100 or 200 years and tell us what the concentration of metals in the ocean was at some previous time. Of course, we know climate is evolving, and it's done it naturally in the past, and now due to global warming. And so, again, there's some data on climate change, but what was the salinity of the Singapore Straits 100 years ago? No one knows. There wasn't anyone here to measure it. So you have to find out some other way to learn that. And if you want to project things 100, 200, 300 years in the future, when you only have a few decades of data, you're on pretty shaky ground, no matter how good your model is. So we'll use the annually banded corals to get isotopic and geochemical records of climate conditions and metal histories. This is an X-ray photograph of a slab of a head of coral about this big, might be 20 or 30 years old. So if you take that and make a flat slab of it and put it on a medical X-ray, you see these banding patterns. And what happens is that on an annual basis, depending on growth rates and other environmental conditions, at some points the corals make denser skeletons or less dense skeletons. They tend to do this on an annual basis. And so like tree rings, you can count back year by year by year to get a history. So we have a good chronology, and then things are incorporated, isotopes and trace metals, into the coral reef skeleton, and then you use that as a way to get the history. So now normally you don't take something this big to do a paleoclimate record. You want something that's 50 or 200 years old. And so you go out and find, as best you can, some giant brain coral about this big, and then use hydraulic or pneumatic drill rig to get a core, and then you slab the core and do the X-ray. So this is what we're typically working with. And so Intan Nurhadi and Yanni Tanzil, here in their best Charlie's Angels pose as they're out obtaining this coral core here, which is about 50 years long from Jong Island off of Singapore. And this is the basis of a large part of our work. I hired In Tan because she was recommended to me by a colleague at Scripps Institute of Oceanography, and she had just finished this thesis work here looking at central tropical Pacific paleoclimate records. So using two paleoclimate indices, the O18, which is a function of the temperature and the salinity of the water, and then the strontium-calcium ratio, which is just a function of the temperature. And then, of course, you can take temperature and temperature plus salinity, subtract them to get a salinity signal. And she observed over these 50-year records here in the central tropical Pacific that some sites had increasing freshwater inputs and some didn't change much at all. And she looked at that in the context of upwelling in the climate. So she had the tools to do this paleoclimate work. She chose to go mainly here to the Western Pacific warm pool, Singapore over here. So we're seeing the Indonesian through flow coming through here from the Pacific into the Indian Ocean. Let's see, this is, okay. So this changes over the years, so over the course of a year. So in the southwest monsoon in July, the flow is mainly through the Makassar Strait here from the Pacific into the Indian. But then in the northeast monsoon in January, there's also a significant flow from the South China Sea into the Indian Ocean. And there's an island with corals called Natuna. And so she found a good coral there and created a record of the sea surface temperature and the sea surface salinity from those geochemical proxies. So here you can see here for temperature, the red is the data based on the strontium calcium measurements of the corals, and the gray is the best climatology that can be obtained. Obviously, it's not so much detail early on, but at least there are estimates of it, and you can see they agree pretty well, showing about, over this period of about 80 years, a 0.5 degree to 0.7 degrees rise in the sea surface temperature. And now, with the O18 measurements and the strontium measurements in the same sample, you can also look at the sea surface salinity and see that it had been getting fresher over time. Of course, if you get temperature and salinity, you also get density. And that's important because there's a correlation between the strength of the Indonesian through flow and the density of the surface water at Natuna in the South China Sea. So red is the Indonesian through flow, black is the density. And so now from this coral record, we have 80 years showing that the density has been decreasing, which would be pointing to a weaker Indonesian flow through over that 80-year period. And so we can then work together with Paula and other physical models to say, why should that happen? Does it make sense? Can we understand this? Okay, well, we don't yet, but we'll work on it. Okay, so now I'm going to move on to the trace metals. You know, even though we've known for a half century after Claire Patterson's work that lead is harmful to humans, nonetheless, over and over and over again, we get examples of people ignoring that and doing themselves in with lead. One of the most recent one is the city of Flint, Michigan, that messed up their water treatment plant and led to very high levels of lead in the water and a lot of harm and economic destruction from this. So it's still a significant problem. It's not so much in the open environment. You're going to see that the concentrations are picomolar, 10 to the minus 12 molar, so very low concentrations, but the marine environment gives us the sense of how we have basically polluted the entire ocean with things like lead. And so it serves as a reminder that, you know, we can't just keep forgetting about this. So metals like lead are emitted by high temperature activities, and they go into the atmosphere, and then the atmosphere transports them on Jason Cohen's aerosols to remote regions of the planet. And in the broader Singapore region, you've got, of course, as you've just seen, the Asian brown cloud pollution, local and regional sources. And so different regions are going to have different stories. And just as a quick example, this is what we saw in the region of the North Atlantic Ocean, which had a large amount of leaded gasoline emitted by the United States and Europe, but it came in and then it went away. And so going to corals and then taking seawater samples for the last, from 1980 to 2000, you can see there's a buildup in the lead concentration due to industrialization, and then the big rise due to leaded gasoline consumption, and then the decrease to the phasing out. And because the lead sources are changing through time, you also have an evolution of the different lead isotopes, and that can tell you something about where the lead is coming from. And so it's a very useful tool that you'll see more of today. But if you go to different regions, you see a different story. So if you go to Rhode Island and look at the last 200 years, this is a history where a source of lead that was very common in the United States in the 1850 led to this peak in the lead isotope ratio and then a fall. But then if you go to British Columbia, you see a completely different history. So you need to look at the regions, and they're all going to be different. So, given the Asian industrialization, and we know there's going to be lead emissions. This is a NOAA simulation of the black carbon aerosols being distributed by the atmosphere. So we know there's going to be lead coming out of here and into the South China Sea and Singapore Straits and Indian Ocean. And so in a couple of papers, we used samples from the Japanese expedition to the Western Indian Ocean here, going from Arabian Sea down to close to Antarctica. In these figures, these are sections, depth sections, going from 0 to 5,000 meters in the vertical axis, and then 20 degrees north on the left and 70 degrees south on the right. And you can see here high lead levels in all the surface waters of the Indian Ocean due to that Asian industrialization. And that it also, as you can see here in this profile from this station here at 40 South, these characteristic Asian aerosols in this region of about 1.14 to 1.15 in the lead 206 to 207 ratio, and then other ratios showing similar features here. So we do have this characteristic thing. And then going to the corals, we can then, Chagos Island, Central Indian Ocean, big rise in lead over the last 50 years because of the Asian industrialization. And then that 1.14 to 1.15 ratio in the corals because of the lead that was being used in that industrialization. But then a big anomaly appeared, and Andrew briefly alluded to this. If we look at the 50-year records from Jong Island in Singapore, we don't see that 1.14 to 1.1567 lead. Instead, we see something that's 1.18 to 1.20. And that's in contrast to what you see in Western Sumatra here and at Chagos Island in the Central Indian Ocean. So what's going on? Is this some local source to Singapore? Probably not. If you look at aerosols in Singapore, we collected on the building of CREATE and S16 for 2 years, and you can see here it's kind of in that 1.14 to 1.15 ratio here, and pretty constant, not constant, but always in that range. Whereas if you look at the seawater in the Singapore Straits, it's 1.2, just like we're seeing in the corals. Okay, to try to get a little bit more temporal history in this, we went to the McRitchie Reservoir and measured a sediment core for the lead. The reservoir is relatively pristine, as any of you have been out there walking around it know. Of course, there's a little bit of housing and stuff, but mainly not too much in the way of industry. And so it's going to basically be a trap that collects the aerosols from out of the atmosphere and leaves a history of what's been in the aerosols. So here now, in a sediment core that covers about 100 years, you go from the beginning of the reservoir in 1891, where you have this red soil, which has a lead isotope ratio that's just the natural ratio of this part of the Earth's crust and very low concentrations of lead. And then from 1900 up until the mid-century, increasing. And then in the corals, you see that, and then finally the decrease as we phased out leaded gasoline. But again, the lead isotope ratios are all poised here in these low ratios that are characteristic of Singapore aerosols. So why does Singapore marine waters, corals, have this high ratio? Is someone from the United States coming out and dumping lead in Singapore Straits? Probably not. So that's the problem that was posed to us. And eventually we've figured out in a study looking at the interaction of natural particles containing natural lead with the industrial pollution that we took a sample from the Johor River estuary. Yes, okay. And we measured the lead and the lead isotope ratio in the dissolved lead and in the particulate lead. And then we took that bottle of water and added a spike of lead isotope ratio that was very different from what we saw in the natural sample. So we took that bottle from here, which is the initial dissolved lead isotope ratio, down to here by spiking it with this isotope ratio. And then over a period of a few hours to a month eventually, you see the ratio rose back towards the level here. And the basic premise of what's going on then is that there is a natural equilibrium between the dissolved lead in the water and that sticks to the surfaces of particles. And the particles coming down from the Johor River are mainly natural lead that's been weathered from the Earth's crust. So the minerals that lead are in are very unstable. They react, they dissolve, they stick to the surfaces of whatever particles are left behind. And so the particles that come down from the Johor River have a crustal ratio of lead 206 to 207. But then when it sees the industrial lead from the aerosol fall out, there's an exchange process according to this KD relationship, which relates the adsorbed particulate lead to the dissolved lead. It's basically the same formula a chemist uses in a chromatographic column, very common assumption. And so basically this experiment here is following that kind of behavior. We start off with initial lead composition on the particles, and we make the dissolved very different, and then over time there's an equilibration between the particles and the waters. So here we discovered something in Singapore waters we wouldn't have been able to see in North American waters because the crustal lead, the natural crustal lead, and the aerosol lead is about the same isotopic composition. Here, because they're so separated, it was very obvious that something was going on. Okay, other things, 170-year record of lead in a Vietnamese coral, and other things that are ongoing now. Gonzalo Carrasco will be showing you a few of these things in the next talk. We have started looking more into the variability of lead and lead isotopes and other trace metals around Singapore and in the region. So we have samples from all of these places here around Malaysia and in Borneo. And so that's coming up, no data yet. And then thank the team members who contributed to this work, and it's been a very good time working here, and I'm glad I was able to work with all of you. Thanks.
Thank you, Ed Boyle. So I'm going to take over the second part of the chair. Yeah. We do one question.
One question. There is 1 minute.
Exactly.
One quick question. Where we present, there is some
Maybe I can ask a question,
Yes.
if nobody wants.
Fine. You go ahead.
So, can you elaborate on the technique used to measure these isotopes? How difficult is it to get these very tiny concentrations just right?
Well, there are very sensitive analytical instruments called multi-collector plasma mass spectrometers. They use a plasma that you introduce your sample to as a fine spray. It ionizes all of the lead, And then you go into a high vacuum system where mass spectrometers separates these. Danfeng Wang here at NTU has one of these instruments. They're very sensitive, but the trick is how to process a seawater sample from the moment of collecting it to getting it to the instrument to make the measurement. The instrument works fine. You buy them, they work, but there's a lot of work and knowledge in learning how to get from picomolar levels in the environment to a sample that you can actually make the isotope ratio measurement by the plasma mass spectrometer.
Right. Good. So,
So there may be 5, 10 groups in the world that can do things like this.